Hey everyone, welcome back to another lecture for Astro421. Today, lecture 6 will be a continuation of our lectures on opacity. So let's start by reviewing a little bit about what we talked about last time in lecture 5. So last time was about the primary sources of opacity within stellar atmospheres. And this is primarily absorption and scattering. And so we've already talked about absorption a lot in lots of lectures. So these are the processes by which electrons move between energy levels in the atoms, primarily. And then there are sources of scattering. So when photons get redirected, sometimes in a wavelength-dependent manner. So there were lots of sources of opacity, both in absorption and scattering we talked about. We also talked about the concept of opacity from a mean free path standpoint. So this is the typical distance that a photon can travel, or that a particle can travel through a medium before it has a collision or an interaction or an absorption or a scattering event in the case of photons and electrons, and how this mean free path relates to the construct of opacity, the sort of the darkness, the transparency of a medium, the opacity. And finally, we introduced a term called optical depth, which is usually written as tau. And this is, again, the sort of average number of path lengths that a photon is going through in a medium. So an optically thick medium is something where the photon can't get through, so no light gets through. It's thick, it's dense, it is opaque. Whereas optically thin is something that's transparent and the photons can freely move through it, or there are very few mean free paths of material there to block the light. So this is kind of a high-level overview of what we talked about last time. Today I want to start putting these concepts together, and we're going to start by talking about what's called continuum opacity. Now I think we used this phrase already, continuum opacity or continuous sources of opacity. So these, by definition, are sources of opacity that work over wide wavelength ranges. So things that are either wavelength independent, like Thomson scattering, those perfect collisions that are just wavelength independent and don't have any lambda term in the cross-section for scattering. Or sources of opacity that have really wide wavelength ranges. And so you might think about bound-free transitions like photoionization. So this are our friends, the Balmer break, the Lyman limit, the Paschen pause. So these limiting wavelengths where any photon with a wavelength shorter or higher energy than some limit will ionize the electron off, and thus will act as an opacity mechanism over huge wavelength ranges. That's what causes these big break features that we see here in the spectrum. And then also also free transitions, so electrons that are floating out there, maybe near an ion, and they can redirect or scatter photons over a very wide wavelength range. So continuous sources of opacity are really important because all photons, no matter what wavelength they are, will be scattered or absorbed, and therefore they become really important in terms of measuring the properties of the atmosphere, since all photons get trapped. There's one type of opacity mechanism that we haven't really talked about, one particular source of opacity we haven't talked about, which is mentioned in the book, and it's very famous in the sun and other cool low-mass stars, and that is the H- or H-an ion, the H- ion. So this is kind of a strange source of opacity, and I find it a little surprising that it's so important. It always sort of surprises me when I read about it. But it's really continuous. It's really broad in its wavelength coverage. This is the story of the H- ion. So hydrogen, neutral hydrogen, is just a proton and an electron, right? Just the nucleus, which is a proton and an electron. It's very simple. When we ionize that, you just get a proton. So in its neutral state, the electron doesn't fully shield the proton, doesn't fully shield the nucleus. And so you can have one electron, the cloud of the electron, sort of sitting on one side of the nucleus, and there's electromagnetic potential on the other side that can attract a second electron. It doesn't pack it in like uniformly. It doesn't look like an oxygen molecule cartoon. What you get instead is an electron that is sort of weakly attached to the neutral hydrogen. So you get the second sort of extra electron weakly bound. And so the ionization energy here is written, the ionization energy for that second electron is really low, like 0.7 eV, as compared to the classical 13.6 eV, which is the ionization limit. That's the Lyman limit, right? That's the electron in the lowest state getting ionized all the way off the hydrogen atom. So to ionize this H minus ion, the H anion, to ionize this second electron, the outer one, you can get almost any optical or near infrared photon. So anything with a wavelength shorter than like 1.6 microns. This 1.6 microns is in the infrared. This is like the near infrared. And so any photon with wavelength shorter than that, which is like the majority of the photons at the photosphere of the sun, can ionize this extra electron. It's not called it's photoionization. The electron gets knocked off, but it's also called photodetachment because the electron is only partially attached. It's only weakly attached to the anion. So this is really a surprisingly important opacity mechanism for stars, for cool stars. It's not so important for hot stars because at hot stars, in the case of hot stars, there's so many ionizing photons that the electron never can actually settle down. So you need it to be cool enough for this extra electron to come wandering in and get attached. And these extra electrons usually come from ionized metals. So it also is really important that you have a star that with some metal content, so you can ionize some of those electrons from those metals, and they can be floating around as sort of extra sources of. They can be floating around to attach to the hydrogen ions to become extra sources of opacity. The other reason you don't see it in hot stars is you need neutral hydrogen to get the extra electron. And so if it's too hot, then all the hydrogen is ionized anyways, and there's no way to form it. So what's really surprising is this is actually like the main source of continuous opacity in the outer layers of the sun, in the solar photosphere. And it's actually really important for lots of cool stars. Okay, so this is sort of one of the missing opacity mechanisms. It's written here in the book, it makes the point of writing it as its own separate term, even though it's really just bound-free opacity, right? It's the same thing as this. In practice, there is this concept called total opacity, right? Where you don't just think about just the bound-bound transitions, or usually just the bound-free transitions. When you're trying to think about the state of an atmosphere, how much light it's absorbing, how much radiation pressure it's gathering, what the impact is for like the Eddington luminosity or the maximum radiation pressure that a gas can hold in thermodynamic equilibrium, you add up all the sources of opacity together. And so, right, you need to understand both the ones that are wavelength dependent, like bound-bound, which are extremely wavelength dependent, bound-free, free transitions, as well as the continuous sources like electron scattering. And in fact, this is wavelength dependent, but it's weakly wavelength dependent. You need to add all these together into something we call the total opacity, some like average total opacity. And this is what you'll sometimes see for a gas or for a material for an atmosphere, is what the total opacity of that atmosphere is, which has baked into it this construct of like the temperature dependence or the density or the metallicity or the metal content or the composition of the gas, right? If the gas is super metal rich, then there will be lots of opacity from the metals. And this total opacity, adding all these terms together, is important when you want to understand the ionization state of the atmosphere or the excitation state. So thinking about the Boltzmann and the Saha equations or other factors that impact the total state of the atmosphere, or trying to understand the properties of the atmosphere as a function of density, for example. This is a plot that Professor Eric Egel pointed me towards, which I think is a really good summary of this is the total continuous opacity estimated, or model of the total opacity for the sun, or for a solar atmosphere at G2V. So this is G2, that's the spectral type of the sun. V is the luminosity class, so G2V, that's the G25, that's the solar type. And these are the various, I love this because it's the various forms of opacity that are dominant at various places, at various wavelengths, at tau of 0.1, so right near the surface, right at the sort of upper envelope, so tau optical depth of 0.1. So this is right at the surface where only 10% of the light is blocked, something like that. Oh, right, at that classic 50-40 temperature. You saw this in your homework. This is that classic 50-40. And here's a similar electron pressure that we saw. So you can see that H minus free absorption, H minus bound free absorption. So here over very large wavelength ranges, this is the photoionization bound free, right? So this is where it goes from free to bound free. So here's anything bigger, shorter wavelength than this. What did I say? 1.4 microns, something like that. Anything. So I guess this is in angstroms. I should say angstroms here. Anything shorter wavelength than this, and this is the opacity curve just from the bound free, the ionization of H minus. And then you see other forms at very short wavelengths. Rayleigh scattering does actually become important for a short little while. And then there's more opacity. There's these little funny jogs from particular elements that have transitions, which make bound-free transitions or bound-bound transitions for those particular elements that cause little jogs in the opacity curve, and then you get the Lyman edge where the opacity is very high out here because of anything higher wavelength short wavelength than this, higher energy than this, 912 angstroms or whatever the Lyman limit is, that Lyman edge, anything above that, and it's almost completely opaque to that. It ionizes anything that's available. So this is the total opacity of the sun. So very similar to the total opacity, but this is something that your book talks about, is the mean opacity. So the total opacity is a function of wavelength and temperature and composition. But if you want to average this opacity over all wavelengths, say the total opaqueness of this gas to all photons coming through. So if you've got a simulated atmosphere, for example, where you understand the temperature and the emission sources in the gas or of the star, and you want to talk about the total opacity of all the gas, so how much heating, for example, how much pressure is going into that gas from that heating, you want to average that over all available wavelengths. And so this is usually written as kappa bar. So this is often, this is definitely an astronomer thing, and sometimes in physics, when you write the average or the mean, you would write a bar over it. Sometimes averages can also have brackets around them, but the bar over there is the notation for average. So the average opacity, when you're combining the total opacity from all photons, you take the average as a function of wavelength or frequency. So the most common form of this wavelength averaged opacity or frequency averaged opacity is the Roslin mean opacity, which I'll talk about in the next slide. But it is also closely related to the Planck opacity, the mean Planck opacity. And you can look at the Wikipedia page, has a nice description of the difference between these. They're very similar calculations, but they use a different averaging scheme as a function of wavelength. So the Roslin mean opacity is the most famous one for stars. So let's just talk about that briefly. And this is similar to the notation you see in the book here. So when you want to estimate what the mean opacity is, you take this average of all the opacities, all the opacity sources, times the spectrum, times the derivative of the black body. So assuming a black body curve for the gas, and that's divided by the average, or divided by this weighting average here, divided by the derivative of the black body temperature. So this sort of adding up all of the opacity as a function of wavelength, the opacity times the spectrum. So it's weighting the actual amount of light that might shine as a function of the opacity. So you've got the opacity, which has, here we have it in frequency units. Opacity is a function of wavelength or frequency times the light that's also a function of frequency and temperature because it's a black body. So this is like the total amount of light that is absorbed in opacity divided by the total amount of light. And it does it as a function of the derivative of the Planck function with respect to temperature. So this sort of funny way of averaging is called a harmonic mean. You see this kind of integral on top, integral on bottom for an average. You see this from time to time when you're averaging over things with, like when you want to numerically average something. This is pretty common. This is the Roslin mean opacity, and I don't think we're going to ever have to calculate it in this class, but you'll see the mean opacity cropping up in things. And I guess I want to close the loop on mean opacity by talking about how mean opacity can be thought of in terms of path length, right? So when we take this mean opacity and we go back to the very first equation we saw in the last lecture, which is relating this sort of mean free path, typical path length the photon travels, relates it to the density and the electron density, or the electron density in the cross-section of the scattering thing, or the opacity and the density of the gas. This is a good way of talking about the typical path length of all the photons. And this is indeed where you see this sort of wavelength averaged or frequency averaged. So it combines all sources of opacity and all wavelengths as a function of temperature. And so it's this as a function of temperature thing that's really key, because you end up seeing this opacity essentially numerically computed as a function of temperature and composition and all the other things that matter. This opacity and the density, which is also a function of temperature, these things go together to give you like a mean free path, or let you start to put this together, and you start to understand how the density and the electron density and the mean free path changes as a function of temperature and density in the atmosphere. You start to be able to study the opacity inside the star. So we'll see these kinds of relationships crop back up in a couple weeks when we start talking about the equations of stellar structure, which describe the density and the radius and the properties within the star, the sort of mean total properties within the star. Okay, Roslin mean opacity. I want to spend at least a minute just talking about this kind of non sequitur, in my opinion. It's kind of a non sequitur, but there's this notation called mass fraction. So this is sort of a left turn here. But if you are reading along in Chapter 9 in Carolyn Osley, the Big Orange Book, Bob, if you're reading along in Chapter 9, specifically 9.2, they're talking about mean opacity. They're talking about averaging all the sources of this sort of total opacity. And they're talking about how that is impacted as a function of metallicity and composition of the gas. I.e., if you have more metals, you get more scattering. You get more electrons floating around to create H minus. You get more opacity. Metals are really opaque, or whatever. So they have this construct, this notation called mass fraction. It is like classic astronomer nonsense. We've already spent a much time talking about Fe over H as this like difference of the metal content relating to as a function of hydrogen in logarithmic units relative to the sun, right? There was this sort of convoluted definition of bracket Fe over H. So here is yet another way, and then we also had M over H, which is sometimes the metallicity. Yet another way of describing the metallicity, which is called Z, with this great formula that even I can remember, which is X plus Y plus Z is 1. This is the mass fraction, the fraction of the mass of the gas of the star that is in hydrogen, plus the fraction of mass that's in helium. So star is mostly hydrogen and helium, and then a bit of metals, like a small amount of metals, right? So like by mass, the star is predominantly hydrogen, more than 2/3 hydrogen, like 3/4 hydrogen. And then only like 1% of the star by mass is in metals. So X plus Y plus Z by construction is 1. This is often written in the literature. The metallicity of this gas is Z of whatever. And indeed, you've already engaged with missed isochrones. Missed isochrones, you type in an Fe over H when you're selecting your isochrone for your stellar cluster. And they make the point that Fe over H is Z, which they mean to refer to as I think Z over H just means like Z. Like it's the amount of metallicity, the amount of metals relative to hydrogen. So I guess it's literally Z over X. I don't know. This Z over H does not quite make sense because Z is like the total fraction of metals. I'm not sure the units here are exactly sensible. but they define some solar Z, right, which is something like 1%. And the same thing for another very famous isochrone set called the Parsec isochrones, which are run out of Italy, out of the University of Padua. And in these isochrones, you pick metallicity by picking M over H, which they define to be Z over. They write this out. They write this out correctly, I think, which is this is like Z over. This is the Z over X in the deck notation. So yet another way that you will see in the literature, you will see metallicity or metal abundance or metal mass fraction, the amount of metals. And it's worth talking about, like, when you're observationally describing metallicity, the impacts it has on, say, a stellar cluster. Changing this number, I mean, in log units, you change from -1 to 0 to plus 0.5 or something. Those seem like big numbers, but the total change in the mass fraction, the total amount of metals, is extremely small. The total amount of mass in this star that is anything bigger than helium, anything with a weight above 2, is extremely small. And so this is why astronomers put these things in these funny notations, so they can use numbers like integers, like plus or minus 1 or plus or minus a few, because nobody wants to really write out that, yeah, there's only 1%, but this star had 1.5% metal. Like that made a big difference. So it puts it in a more human readable term, but but it is yet another confusing notation. Anyhow, I wanted to address it because it takes up like a page in this chapter, and it harkens back to one of the silly things we've talked about. Okay. So we now have sort of a summary understanding of the source of opacity that a star has from continuous and limited wavelength ranges, both in bound and free transitions, scattering and absorption, right? Lots of sources by which photons can get deflected or absorbed or have their energy changed. And I thought in the next few minutes we should spend, I guess, the rest of this lecture talking about some observational examples or some physical examples where opacity is important and the concept of opacity and optical depth are important. And the first is one we've already talked about in the last lecture, and that is, again, like the most important construct to know optical depth, in my mind, is when considering the definition of the surface of a star. Because again, a star is not this hard physical, it's not a rock. It doesn't have a well-defined surface. But instead it's a gas, right? This atmosphere is a gas, and so it has a tenuous outer boundary that sort of peters out. And that's why we have to define a radius. At some point you have to measure the radius of this thing and define it. And so, ergo, we use this definition of optical depth. So optical depth by construction, the boundary condition is there is nothing to absorb the photons at the ultimate surface. So at the surface, optical depth should be 0. Or like outside the star, at the boundary outside the star, the optical depth is 0. As the observer, you're in the optical depth 0 range. And we can see light that reaches down to about optical depth of 1. So like 1 typical path length through the star. This is heavily wavelength dependent. That's why spectral lines are a thing, because those ones block a lot of light at those very specific wavelengths. The photosphere, we talked about this before, the photosphere is classically defined as the depth in the atmosphere where you achieve tau of about 2/3. About 2/3. Why that number? Because e to the minus 2/3 is about 0.5. It's not 2/3 exactly. It's like 0.2. It's like 0.667 or what? 0.677 or something like that. I forget, but it's about 0.5. And so, i.e., this is the depth that you can go into the atmosphere and have half of the light that is shining up from the star attenuated. So half of it is absorbed by the material above it. So it is how far you can go, where half of the light is transmitted. And the further down you go, the majority of the light that is coming from the star is absorbed. So you get down to here. This is like tau of 2/3, and this is tau of 1. This radius is, again, heavily wavelength dependent. This photosphere, the depth in which you can measure, is wavelength dependent because of the various opacity mechanisms that absorb light that are not perfectly continuous, that the opacity of the atmosphere is not flat. And so, ergo, the radius that you imply for the star or for the sun is different as a function of wavelength. If you look in very limited wavelength channels where there are places where there's really high opacity, you would imply a big radius for the star. This means, since opacity itself is really metallicity, composition dependent, that the composition impacts the radius. This also means, because metallicities are sources of opacity, to back up, metallicity changes the radius that you measure. It also changes the actual radius of the star. Metallicity, more metals create higher opacity. This creates typically increased absorption, and therefore the gas in the outer part of the photosphere will have more pressure on it from below the star, and then to remain in hydrostatic equilibrium, it moves out. And thus you get a bigger radius, and you lower the overall effective temperature. So metallicity, metal lines create these absorption features in the spectrum, which make the spectrum look redder for the given effective temperature, and they also absorb the energy of the photons coming up from inside the star, and so they actually do create an atmosphere that's a little cooler, a little puffed up. So the metallicity really is even a small amount of metals can really impact that outer opacity, and thus impact the radius and the temperature of the star. So this is the subtleties of the surface of the star. There's another area where defining the surface of the star is really important, and is very popular, and you have doubtless seen graphs about this, whether you knew it or not. And that is this idea. So one of the most classic examples in talking about optical depth is limb darkening. So the sun does not appear to have a uniform brightness across its disk, across the surface. We would call this the solar disk. You look at the sun. This is an actual picture of the sun from Solar Dynamics Observatory. This is not modified in any way. And you see that the outer limb, what we would say is near the limb, which means the outside edge, near the limb of the sun, the outer reaches of the sun, it is darker. And in the middle, it is brighter. So you see there's like an average brightness, surface brightness variation. You also see this in the temperature. This is a single band, but if you were to make a color, say this minus, so the B minus the V pictures of the sun, you would see that the outer limb of the sun is redder, looks cooler than the inner portion of the sun. But this doesn't make any sense because the sun is a sphere, right? Like, it's not like the sun is cool on this outer shell, because if you move to the side, you'd see the same thing. This is an illusion. The sun is uniformly, to first order, the sun has uniform temperature on its surface, but we don't see a uniform sphere when we look at it. And that is because of something called limb darkening, which is a consequence of opacity. When you're looking straight at the sun in the center here, so straight in the middle of the sun, or this arrow here, the optical depth of 1 is this hot level. It's whatever optical depth of 1 is. It's the 5700 Kelvin, 5800 Kelvin gas that you see right here, almost 6000 Kelvin. When you start to look near the limb, to get enough absorbing material to actually see the surface, the place where you define an optical depth of 1, you need to go through a bit more material because it's cooler, because you're looking at it at this angle. It's this viewing angle effect, which is geometric, right? So this is due to the geometric distortion of the atmosphere, because you're not looking at a flat thing, you're looking at a curved thing. And you're looking at this partially transparent curved thing. And so this is the same. This is kind of the opposite of the idea of air mass, where when you look at when you're looking straight up in the atmosphere, you're looking through the least amount of the Earth's atmosphere as possible. When you're looking towards the horizon, you're looking at the maximum amount of the atmosphere possible. And the same kind of thing here. You're looking through the maximum column density of the cool gas on on the surface of the sun or in the outer envelope of the sun. And so you hit a tau of 1, you hit optical depth of 1 when you're in this cool lower luminosity gas, and that's why it looks cooler and it looks fainter. So that's limb darkening. That's why limb darkening happens. It's a geometric effect of the curvature of the star. So one place this is incredibly important is in observing transits, particularly for exoplanet transits. So to first order, you can assume that the exoplanet is opaque. Now, we will not assume that soon in the future in the era of the JWST, but to first order, you can assume that the planet is just this opaque little thing moving across to the surface of the sun, blocking light. And as it does, it blocks. This is like spherical geometry, circle blocking a circle. It blocks the amount of light that it blocks is due to the area of this circle divided by the area of this circle. Except for the thing it's blocking is not a uniform surface brightness thing from our viewing angle or from the projection of the planet. And so instead of just seeing some like top hat shaped thing or some like bucket shaped thing, an actual transit light curve has this slow ingress is due to, at first, the planet only blocks this little edge, and then by the time it gets here, then the planet is fully blocking the disk, or is fully on top of the disk of the star. And then what you see as it travels across the surface of the star is it's not truly a flat bottom in the transit. It has this curvature, and this curvature is the planet blocking limb darkening light that's limb darkened. So this is like real data. These dots are real data, and this is like an extremely high quality giant planet around a very, very bright star. But this is extremely important. It both determines, especially during the ingress and the egress phases, ingress and egress is what we call it. This limb darkening profile, the equation that defines the difference in surface brightness from the center to the limb, but it also really strongly affects this curvature at the bottom. But this shape is dramatic, and this shape is subtle. So if your planet is very small, you might not be able to see this, but you will be able to see this ingress and this egress. So it is really important. The industry standard, what everybody uses, is called the Mandel and Agol model, which was written in 2002. Agol, the name should be familiar for you. This is Eric Agol, who is a professor here at UW Astronomy. This paper is an extremely important paper. Since it's been around now 20 years, it has something like 1,500, 1,600 citations, because every piece of code, every person who studies exoplanet transits, which a lot of people have in the last 20 years, use this model because it is extremely good approximation or description of limb darkening, and it does it all analytically. And this is why it's so powerful, is that it doesn't take some measured model from the sun and apply that. Instead, it uses the solar model and it fits analytic functions. So like some series of like sinusoids and things to describe, so things that the computer can calculate very efficiently to describe this curvature. And so these are different, you can see these different curvature profiles for different limb darkening laws that you could construct for a theoretical star. This would be the egress profile, but it's symmetric. Ingress or egress is symmetric. So you can see this one has no limb darkening, this solid line, so it's a flat curve, no limb darkening. It's a perfectly uniform sphere, so it's a flat transit. And then the only curvature you see here, this little curve here, this is just the geometric effect of the two circles passing off each other, or passing onto each other. And then as you slowly increase the importance of limb darkening, you can change the, so this is the flux, the absolute flux of the star is 1, And so here is limb darkening up to 2%, right? So this is a difference of 1%, but look at the dramatic difference of the shape of the light curve. So this is the industry standard. There's lots of codes that you can use. These equations you can write down. They're not impossible to write down, but you don't have to write them down. There is some great packages that have the Mandel and Egel model already coded up. There are some other models besides this, but this is the one to keep in mind. And if you're coding in Python, there's a nice package called Batman, which is a transit model that uses the Mandel and Egel equation. So if you're on the slides, you can click on this link, but you can also just Google Mandel and Egel transit model. And this is so important that people, we care a lot about it because exoplanet studies, exoplanet discovery is a big field right now. Here's two examples. That should say 2018. That's a typo. Here's two examples of fairly well-studied exoplanets. This one, Trace 2b. I think these are both. I think this is a hot Jupiter, and this one I don't remember. I don't remember offhand what Kepler 425b is. But these are just two examples from the dozens from this paper that is particularly focused on the impact of limb darkening models, and you can see. So here is the actual data. The blue dots are actual measurements mostly from the Kepler Space Telescope, and the red curve is the Mandel and Egel model. They've normalized any other brightness from the star out, so it's normalized again to be 1. And just like in the model here, you get, these planets happen to be the right size. So this is a 2%, 0.98. This is a 2%. So this is about the same 1.5%. Dip in the brightness. This one is about the same 0.98. You can have planets up to several percent. You can have in terms of flux that they block. And again, the amount of flux you block is related to the ratio of the radii of the planet to the star squared. It's the area of the planet divided by the area of the star. But you can see the success of this model. Like, look how good this fit is. This is the blue dots minus the red curve is this residual here, and you can see it's an extremely good model. The limb darkening profile, you can see just the limb darkening in action. You can see this is a non-uniform brightness sphere that this planet is going over, which is totally fascinating. So limb darkening is a thing, and it works, and it's a consequence of opacity. And it is a function of wavelength. And here is a great example. This is spectra. So these are two spectra that need to be calibrated onto each other. So this is one star, but this spectrum should actually kind of smoothly go through these two spectra here. But this is an illustration of the spectrum as a function of wavelengths. You get they chunked this spectrum into lots of wavelength bins. And here they're showing the transits, the exoplanet transits for this hot Jupiter, HD 209458b, this hot Jupiter that went in front of a star. So hot Jupiter, so it has like 1.3 times the radius of Jupiter or something like that. And so you can see the transit profile is not exactly the same. You can see here in the red wavelengths here, the limb darkening is less significant. Because the opacity, so the star looks more like a uniform disk in the infrared, and so the limb darkening is less substantial. It's much flatter. It's not perfectly flat, but it's much flatter. Whereas out here in the near UV, around 300 nanometers, you can see that the limb darkening profile is really substantial, that you go from ingress and it just keeps changing. It never hits this sort of uniform disk and the uniform sphere, brightness object. And this is a nice example as well of the models of the limb darkening profile as a function wavelength sort of stacked on top of each other. It looks like kind of a cool butterfly or something. But you can see the wavelength dependence is drastically different. And so if you were to just use one of these curves and just sort of take this measurement, and especially if the noise, this is an excellent example where the signal to noise of the data is superb. Right, this is like best possible data. But if you had a noisy example where the noise here is sort of scattered, you might imply, if you just had one of these bands, you might imply a certain radius for the planet. You might sort of take this average depth here relative to the out of transit depth, and you might imply a certain depth of the transit which does not match the depth that you would get from a different wavelength. So you might imply the wrong radius for your planet. So if you're trying to characterize exoplanets, you got to get this limb darkening right. And then you can read this paper and see that they're saying that at certain wavelengths, the model is wrong, that there are still deviations from the model that they can see with really high signal data, really high signal noise data. Some of those could be due to the composition of the planet. The planet itself has an atmosphere, and that atmosphere, it is not a simple opaque disk, but the planet itself has an atmosphere whose radius is wavelength dependent. And so if you were to take lots of transits at different wavelengths and you understood the properties of the star and the limb darkening and the opacity of the star and the composition of the star really precisely, then you could subtract off that perfect star model and look for deviations in the depth or in the profile here that would be due to changes in the planet's radius as a function wavelength. And this is the concept behind transit transmission spectroscopy, which is the idea that the certain amount of light is actually transmitting through the planet's atmosphere as well. It's getting through the planet's atmosphere. The planet is not a homogeneous black, just uniform darkness thing, but itself has its own opacity at work. And so for giant planets, this has been successful in terms of looking for indicators of planet atmosphere chemistry. Very interesting. But this is all anchored on the idea that you have a perfect model for the star, that the star is just a matter of the opacity, the scattering, the absorption, the composition. And if you only knew the opacity and the temperature and the density of the star, then you would be able to have a perfect model. And this too is an imperfect approximation because stars are not uniform brightness things. In fact, some stars have really non-uniform surfaces. So if we go back a few slides, here's the sun. There are these little dark spots on the sun, these little pairs of dark spots. You can see there's a little cluster here. Here's a small spot. Here's a big spot group, spot pairs. These sunspots, while small and sort of transient, they come and go, they can be really, really frustrating when you're trying to study exoplanets. And that's because as the exoplanet passes in front of the star, it is, once again, not passing over a uniform brightness thing. It is passing over these cool, dark spots. We can talk about the physics of why star spots are dark is not an opacity issue. It's due to the convection being inhibited. It's a pressure from the magnetic fields. Spots arise from magnetic fields. These are just cartoon spots. These are circles that we just dropped on the surface of this pretend star. So you can see as the spots roll around, you get this modulation. As the star rolls around, you get modulation from the spots. But as the planet crosses those spots, the path that the planet maps out across the surface gives you some map of the temperature or the flux contrast on the surface of the star. And so you can see really large variations, bumps in the transit as the planet passes over these cool spots. This is a cartoon of how this effect works. This is a cartoon I made during my thesis work, but this effect has been observed in stars and has been studied actually extensively by many people, from stars for like HAT P11, Kepler 17, Kepler 63, a bunch of stars where this effect has been used to study the star spots themselves. But again, this is a huge pain in the butt if you really care about studying the planets, because here is extra noise that changes from transit to transit. And so if your observing campaign relies on going and observing at one wavelength and then another wavelength and another wavelength to build up this nice stack of data, you better hope that the star looks exactly the same every time the planet passes in front of it. Because if it doesn't, if spots are coming and going, you're going to get different depths, and it's going to really make you unhappy. So, and you can see here's limb darkening here at the bottom on top of it all. Okay, so that's enough about limb darkening and the surface of stars and the radius of stars. Let's just spend a couple more minutes here at the end talking about some examples of scattering and absorption, so opacity mechanisms at work. One source of scattering that I didn't talk about because it's not super important in the outer atmospheres of most stars, it is for very cool stars, but not for most solar-like stars, is Mie scattering, which is like Rayleigh scattering and is wavelength dependent, but it occurs for very big particles. And this really matters for dust. And so here is like one of the best examples of scattering, particularly me scattering at work. There's like Rayleigh and me scattering going on here. And that is what's known as the Pleiades nebulosity. So you can't see this by eye. This is the Seven Sisters. This is Pleiades, Subaru as it's known. This is a very famous set of stars, young stars, something like 120 million, like 100 million years old, very young stars. And when you observe them with a telescope, by eye, you can see there are multiple stars. You can see it's a little cluster of stars. But if you get even a good pair of binoculars or a small telescope, you can see there's like extra glow around them. And this glow is not just due to the stars. These rings around the stars and these spikes, these are diffraction and optical illusions due to the telescope. They're not real. But this wispy, ghostly structure here is real and is well studied, and it's called the Pleiades nebulosity. And it is gas, cool gas, that is moving through the cluster, or the cluster is moving through it. I'm not actually sure if the cluster is on an unusual orbit, if the gas just happens to move. Like, I'm not sure who's moving through who. But what's really interesting is it's just coincidence that we see this nebulosity, this wispy structure around these stars, and they are glowing through them and lighting them up. And so the reason these wispy clouds seem to glow, that looks so eerie and so wonderful, is because they are scattering light. And so the nebulosity we see, the structure we see, is due to photons that left the star going sideways, getting scattered and directed towards our line of sight. When you take radial velocity of this gas, which is hard to do, you can see that it's moving relative to the cluster at a few kilometers a second. So not super fast, but these stars are traveling as a group through this medium. And it's just luck that we see this beautiful nebulosity. It's really fun. But this is scattering at work. Scattering is really important when talking about dust and the interstellar medium. But also just good old-fashioned absorption is really important as well. And really strong absorption is the name of the game when you're looking at these really dark dust objects, dusty clumps, these like little clouds. It looks like somebody came and like cut a hole out of the universe. And these are known as Bok globules. It's a really just lovely word to say, really, really pleasant in the mouth. Bok globules. They are very effective absorbers. These are extremely cold gas, so cold and so dense that like light does not get through them. They are just like perfect absorbers of dense cold gas. And like one of the ongoing areas of research is, how do you get gas to be this dense and this cool? Like, what are the cooling mechanisms by which regular interstellar medium gas collapses down? Because when you collapse gas, it tends to heat up. So how are these things cooling enough to form these dark globules? These globules are thought to be the precursors to star formation, that you would see a few solar masses of material in this globule and it would collapse down into a protostar on the order of millions of years. And so what you're seeing here, that's why there's all this wonderful nebulosity and reflection going on and scattering going on, because you're in the middle of a star forming region here. I forget which star forming region this is. I should have grabbed that caption. You're in the middle of this lovely star forming region, and this is an especially dense pocket of gas. The best example of a Bok globule, in my opinion, is Barnard 68. And it really does just look like somebody came through and like cut a hole out of the galaxy. You just see this like little gap. There are no stars there. This is Barnard 68 in the optical. Here it is in the sort of middle, the classic of the V band, 55.5 microns, 550 nanometers. And then as you start to get into the red, you start to see the globule starts to shrink. And so it goes this way. And then here it is at 1.2 microns, 1.6. This is like J, H, and K bands in the infrared. And at K band, no evidence of the globule at all. And this is because, and you can see stars, it does look like, okay, there's a little evidence. There's like a slightly lower density of stars here. Or the stars that are here are slightly fainter still. And that's because this is like the extreme example of what we would call dust extinction, or light being attenuated, light being absorbed and scattered, mostly absorbed in this case, by very cool gas, very cool dust. And in the infrared, the absorption is less efficient. The scattering and absorption mechanisms are less efficient. And so the opacity is lower in the infrared, and so you can see through it. In fact, some of these stars you see in some of these globules, you will actually, if you look deep in it, you can see the protostar inside of the globule in some cases. So I love this example, opacity at work. So these two examples of both nebulosity, being reflecting and scattering light out, and globules absorbing, these are two examples of why this field is important. So in the field of observational astronomy, this whole concept of absorption is really important in understanding dust extinction and modeling dust extinction. And this is notoriously difficult to do with any precision. And that's because we generally can't go out and collect samples of this material. We don't know what this dust is really made of. The Stardust mission gave us some hints of what this dust is made of, but not a wide sampling. What we see when you model the absorption, the extinction as a function of wavelength of interstellar dust, you take lots of spectrum of stars and you subtract off what you think, or you divide out what you think the true spectrum is. You do this many, many times. You can build this model of what you think the this absorbing gas and dust is in the way. You build this wavelength dependent model, and you see it's extremely smooth. And this is not a function. This is not due to poor quality data that we don't see fine structure here. It's that we really just see really smooth absorption or extinction as a function of really all wavelengths. So this tells you that continuum sources are at work. And we know that this material has got to be really cold generally. And so this tells us, and it's most likely due to like molecules and dust and clump. Dust is just like giant molecules. And so we know that these features, these transitions, these bound-bound and bound-free transitions are really, really broad. And these rotational, vibrational modes that these molecules will respond to photons are extremely broad, and like any photon can upset the dust. And so as a result, you get this really smooth extinction curve, which is just like essentially the opacity curve of the material. So we think this dust is made of lots of molecules, lots of chemistry at work. You'll hear people talk about they discovered sugar or alcohol or your favorite hydrocarbon in the universe, and it's often in this interstellar medium. A lot of these features are due to silicates. This bump here at 10 microns is due to silicates. This is also silicates. There's a bunch of polyaromatic hydrocarbons, PAHs, at work, but it gives you this sort of general curve, and this is in magnitudes here. This curve is very smooth. Again, continuum opacity is at work. It's very important at short wavelengths, so there's lots of opacity at short wavelengths. Again, kind of like me scattering. It's not so important in the infrared, though it is important. Like it is unfair to say that it is unimportant in the infrared. And there are, as an example, at 10 microns, this is well past your visible. This 10 microns is mid-infrared. There is a bump, like the opacity of the interstellar medium increases, and you see more extinction at 10 microns, which is interesting. One reason, we talked about this, I think a week ago, astronomers have a hard time talking to each other by units sometimes, and one great example of this that drives me up the wall as an observational stellar astronomer, I look at things as like flux or absorption as a function of wavelength, sometimes frequency, but usually wavelength. In the studies of the interstellar medium for historical reasons, they usually compute this as 1 over the wavelength in inverse microns. This unit blows my mind. I would love to hear somebody tell me why this is a good unit, why this is the right way to measure it. But what it does do is emphasize variations in different models, different chemistries of dust that you might be looking through. And this, so big 1 over wavelength here is short regular wavelength. So here we are. So this bump here is this little bump here at 0.2 microns or whatever. You can see different models that use slightly different chemistry for dust grains give you wildly different absorption in the ultraviolet. So here you are, extremely short wavelengths, ultraviolet. And so this R is the reddening law that we assume. R of 3.1, it's like right here. It's like this, like right above this curve here. R of 3.1 is the classic R. We can talk more about how you define R and how you use that in terms of A, and from an observational standpoint, how you actually use these numbers. But we see most gas in the Milky Way appears to have an R of 3.1. There are places where the R is clearly different. And so near certain stars or in certain star-forming regions or near certain globules or dust clouds, you will see that the extinction that you can back out from modeling the spectra of stars or protostars looks very different. And that's telling you that the chemistry of the dust is different. This is a circular problem. If you want to really understand, especially at short wavelengths, the spectra that you're observing of the star, you have to understand the chemistry of the dust. And so if you really care about continuous opacity or continuum measurements of stars in the ultraviolet, you have to have some independent measurement of your dust. This is a chicken and egg problem, and it has confounded astronomers for a long time. There is a lot of ongoing work here. Interstellar absorption of dust. Okay, a couple more examples of opacity at work. One that I am endlessly amused by, this is a nice cartoon of asymptotic giant branch stars, AGB stars. They form dust in their outer atmospheres, in the most tenuous, furthest reaches of their atmospheres. The stars get so big, the atmospheres get really cool. And when they get really cool, dust can condense and sublimate and form. And so you get these shells of dust that form because the material maybe moves out from these pulsational shocks. The lower parts of the star are kind of pulsating and burbling for lots of reasons. And so material will kind of move out into the outer atmosphere. And when it does, it cools. And when it cools, that allows the dust grains to start forming. And the sort of dust bunnies start to form in the outer atmosphere. Because, again, they're truly enormous atmospheres. When the dust grains form, the opacity rapidly changes. The dust becomes very opaque. And so you can have a big plume of dust that forms, kind of like a little blob of dust that forms, which can make your star look like it disappeared briefly or change in brightness very dramatically from a dust plume forming, for example. But what also happens is the photons coming from the lower levels of the star, which are shining upwards, always shining out, will shine on that dust, that newly formed dust, and the dust is super opaque, and so radiation pressure shoves that dust, and what you get is radiation pressure ejecting the dust, and so you get this dusty, clumpy, continuous, blobby wind coming off giant stars. So not only do these asymptotic giant branch stars have pulsation and convection that can throw material off, but you also can get these dust shells that can come launching off, and sometimes in shells and rings, but also just in like clumps. And so you get this really clumpy ejecta. And so there is a bunch of study about what kind of complex material can come off of, especially AGB stars, due to radiation pressure and opacity driving dust wind. That's really cool. The other example is called the kappa mechanism. Kappa here being your friend and mine, opacity, the opacity-driven mechanism for variability. And so the kappa mechanism, sometimes, I've never heard this, but like you see this in books, sometimes called an Eddington valve, is a heating engine. It's like a Stirling engine or something, like a heating cycle where gas gas heats up and cools down and causes a star to pulsate radially. So you end up getting like a balloon being inflated and deflated almost. So this is opacity-driven pulsation. This is pulsation of a star where the star gets bigger and smaller by some pretty big fraction. And it does this due to an effect of opacity. So the Kappa mechanism works like this. Gas that's in the outer part of the atmosphere falls down due to gravity. As it falls down, it heats up. It compresses and it heats up. And it increases its opacity with temperature. I'll come back to this point, but this is what happens. It increases the opacity. When this happens, the material becomes more opaque, so radiation pressure starts pushing on the gas. The gas wants to maintain hydrostatic equilibrium, thermodynamic equilibrium, so you push on it, and it's going to expand. It pushes the atmosphere out. The atmosphere goes back out. It cools. the opacity drops, and the cycle repeats. And so you end up getting this opacity-driven pulsation where the atmosphere heats up, expands, cools down, contracts. And it does this pretty significantly, 10% changes in radius even. Pretty substantial changes in radius. Now this is a little backwards, as I've indicated here, as what you might expect. Where as you increase the temperature, you would think that the opacity would decrease, as it does for like regular run-of-the-mill neutral hydrogen. You increase the temperature and its ability to scatter photons decreases, but this is why the sun doesn't pulsate radially like a balloon being inflated and deflated. Instead, this opacity mechanism flips over, the temperature dependence flips over, and goes backwards to what you'd expect due to ionized hydrogen or ionized helium. So partially ionized helium or ionized hydrogen can have the opposite effect on opacity that you would expect. And this happens, there'll be a little shell inside the star, this sweet spot of temperature and density and pressure, where you have just the right hydrogen ionization layer inside the star. And so this layer is what's driving. It's not the actual whole outer part of the atmosphere. The whole outer atmosphere is just kind of along for the ride. You get this one layer inside the star which heats up and puffs up. And so the whole atmosphere goes and fluffs up, and then it all comes collapsing back down and falls in on itself. We're going to revisit this whole scenario. So the spoiler here is this is called an RR Lyra star, or a Cepheid variable. There's a couple types of stars, Delta Scuti also, use this kappa mechanism to drive these radial pulsations. There are other mechanisms that drive pulsations, which we won't talk about here because they're not opacity driven. But this is the sort of backwards opacity. When opacity temperature dependence flips over, you end up getting this instability, which drives stars in this radial manner. It's really neat, and we will talk about it again in a few weeks when we revisit pulsators and how we observe them. Okay, and that wraps up our talks on opacity as its own topic. Next time, we were going to start the exciting journey into radiative transfer. Your reading is, as it has been, Chapter 9, and I will see you in a couple days.